Welcome back to ECE 320A. We're in Unit 8, which is the convolution integral, and now we're actually going to work through a convolution example in this particular video, and we'll try to illustrate the steps. We won't go through them real meticulously. We'll actually reserve a couple of videos to talk about flipping and sliding and intervals and limits, but today I want to put all of that together in this video and try to coach you through the process or the steps involved in performing a convolution integral. And we'll do it by an example. Again, we're still in Chapter 13 at the very back side of Chapter 13. Homework 8 is due at the end of this unit, and exam number 3 will occur at the end of unit number 8, which is this unit. Here's our convolution example that we want to work with. We have two waveforms, and I'll try to be consistent with my coloring so that you can maybe distinguish between what's happening relative to x and what's happening relative to h. We want to convolve these two waveforms, which means that we want to use these functional forms in this integral to find what the convolution integral will be, or what is y of t. And y of t is not necessarily just one functional expression. It may be a different functional expression over different intervals of time. And that's why it's important to sort of walk through this process to get a feel or to gain some confidence into what we're doing when we're performing these convolution integrals. Now, you might initially ask the question, which is a reasonable question, a very good question, is why am I worrying about finding or evaluating this first integral equation where x of t minus lambda is used versus where we might use h of t minus lambda, and that's actually motivated by the functional form of x and h. Relative to what I want to do with one of these waveforms, I need to essentially flip and slide it around. Well, to me, it looks like x is going to be easier to flip, and when I say flip, I'm flipping with respect to this vertical axis at time t equals 0. So I'm flipping x or h relative to that particular pivot location. So my answer is, why are we using this convolution integral and not the other? Why are we using the black convolution integral versus the blue? And my answer is that I think it will be easier to what I'm calling flipping and sliding, or I think it will be easier to flip and slide x of t instead of h of t. And the reason I'm thinking it's easier to flip and slide x of t is really because x of t functionally is a constant. I don't have to worry about this up and down or this shape of x as a function of t. It's just flat. So x of t has a constant functional form, and that's what convinced me to use the top convolution integral expression versus the bottom convolution expression on the screen now. So now that we have that in place, let's now start finding what we need to put in the integrand of this convolution integral. We need h of lambda. We're given h of t, and we need x of t minus lambda, and we're given x of t. Well, hopefully you can see that h of lambda is not a challenge to find from h of t. All we're doing is changing the variable of integration, or the variable, the independent variable in h of t versus h of lambda. The variable of integration is lambda. So in this expression, in this convolution integral, t is a parameter that we will move around. H is the integral that we will integrate with respect to. And in this convolution integral expression, we want to now find h of lambda. Well, that's pretty straightforward. H of lambda is just h of t with t replaced everywhere with lambda. And that was now, I said I was going to get my colors right. So that was now 2. And then it trails off exponentially. This is now, and this is important. We need to keep track of what the functional form of these different equations actually are. So in this case, it's 2e to the minus 2 lambda. Now what we want to do is flip and get ready to slide x of t, which means we're trying to generate x of t minus lambda. And I like to do this in 3 steps. I like to first find x of lambda, which is easy because I already have x of t. So I really just have to copy down x of t and change t to lambda everywhere. Doing that, I now have x of lambda, which starts at minus 1 and goes out to 3. And it has an amplitude of 5. That's x of lambda. X of minus lambda isn't that hard because x of lambda is constant in terms of its functional form. Now all I need to do is rotate or flip x of lambda relative to this vertical axis at lambda equal to 0. So that now what was at minus 1 now comes over to 1, and what was at 3 now flips over to minus 3. And I haven't changed the vertical location or the functional form. It's now still a constant of 5. And that's now x of minus lambda. And remember, lambda is our variable of integration. Now we want x of t minus lambda, and t is a adjustable parameter, and t, we are going to allow it to slide from minus infinity all the way up to plus infinity. So in that sense, let's start with t being very small in a negative sense, and let's just now put our x of t minus lambda. Now we're just introducing t into our x variable, or our lambda variable, the independent variable, and we still have a height of 5. But now I hope you can see that this is now ready to be slid around the lambda axis. For example, if we went ahead and plugged in t equal to 0, we better recoup what x of minus lambda is. So if we look at x as a check, t minus lambda, when t is equal to 0, we better get x of minus lambda. So if you plug in t equal to 0 into these locations, then this function will slide over, and the 1 will actually become on the right-hand side of the lambda axis, and the minus 3 will be where we want it, and voila, we do have x of minus lambda. That's how you can start to check your work as you're working through these convolution problems. Now we have all of the pieces that we can put into this convolution integral. We have h of lambda, and we have x of t minus lambda. Now we have the integrand. Let's now figure out what's going to happen. And remember, in this convolution expression, y is a function of t. That's the end result, which means that we need to plug in different values of t on the right-hand side and see what happens functionally to this product of h of lambda with x of t minus lambda. That's why I'm now concentrating or talking about these overlap patterns in case h and x share a common interval of support. So let's now look at overlap patterns. And in particular, let me try to define what I mean by overlap. Overlap of this function, x of t minus lambda and h of lambda, doesn't mean they have to be both positive or both negative. It just means that they share a interval on the independent lambda axis. So overlap of x of t minus lambda and h of lambda occurs when the support intervals of the two functions overlap, or one waveform doesn't have to have one waveform could have a negative functional value and another waveform could have a positive functional value, and the two waveforms could still have overlap of their support intervals. So when I'm talking about overlap, I'm referring to their support intervals. Here I've tried to illustrate that in this diagram. X of t minus lambda, I'm now showing it going from a negative value up into the positive values of lambda, and I've tried to hash that from top right to bottom left on the lambda axis. And this is now the waveform. That's x of t minus lambda. H is this functional shape. And I hope that you can see then that x is supported on the lambda axis in this region of lambda, and h is supported in on its lambda axis over that interval. And what we're interested in is, do these intervals of support, where they are defined, where they have some non-zero value, do those overlap intervals, or do those intervals of support overlap? And that's what I've indicated in the yellow highlight. That's the interval that these two waveforms, x of t minus lambda, in this illustration, where they overlap. And I hope it's clear that their overlap interval does not correlate at all with their functional value. It's just where that functional value is non-zero. Now, let's return to our example and look at x of t minus lambda. And remember, we can fix, or we are allowed to slide x of t minus lambda by the assignment of different values of t. That's our variable that we can adjust. And we already have h of lambda. So let's plug in h of lambda. That's easy on this diagram. So now we have h of lambda. Let's quickly put that in here. And my diagrams may not be very accurate, but there's h, which is now 2e to the minus 2 lambda. And what we want to do now is show where there actually isn't any overlap. Here's the interval of support for h, and it just goes on and on. But now we want to show that in the first case, for a particular set of values of t, this was now t plus 1 and this is t minus 3. Here is now the interval of support for x of t minus lambda. And we want to now determine what particular values of t does this actually occur. When does this occur? Well, this overlap pattern, this particular pattern, and we're looking for unique patterns all the time. This is the first unique pattern. This pattern will occur when t plus 1, the right-hand side of x of t minus lambda, stays to the left of h of lambda, which is starting at 0. So as long as t plus 1 is less than 0, or as long as t is less than minus 1, then y of t is equal to 0, because there's no product, or the product of h and x of t minus lambda is 0. We're multiplying because there's no interval of support where they overlap. So y of t is equal to 0 as long as t is less than minus 1. That's the first overlap pattern, which in this case is no overlap. Let's look at a partial overlap. Again, we can immediately write down h of lambda, which starts at 0 for lambda and goes on to infinity, and here is now its interval of support. X of t minus lambda, now we want to slide that through, and I said we want to look at the next unique pattern, and the unique pattern now is as long as we have this picture in mind, and that picture says that t plus 1 now needs to bump up bigger than 0. So this overlap pattern occurs when t plus 1 is bigger than 0, and we need t minus 3, the left-hand side of x of t minus lambda, to remain less than 0. So now, therefore, y of t has this functional value as long as, and now we could look at this, we could say, oh, this is now as long as t is greater than minus 1 and t is less than 3. And a lot of times I will put a less than or equal to or a greater than or equal to on one of these pieces so that now I can say that y of t has this functional value when t is greater than or equal to minus 1 and less than 3. That's when we have this picture. What we need to do now is try to compute the functional value of y of t. What is y of t actually going to equal? In this case, we have the integral of h. Let me try to color code this again. H is now 2e to the minus 2 lambda, and that's times x of t minus lambda. Well, the functional value of x of t minus lambda in this picture is just 5, and now we need to integrate that with respect to lambda. But now what are we going to integrate? Are we going to integrate from minus 1 to 3? And I hope that it's clear that that's not what we want to do. We want to integrate this based on where we have this mutual overlap of the intervals of support. And that occurs in this picture from this particular value of lambda, which is lambda equal to 0, up to this particular value of lambda, which is lambda equal to t plus 1. And it's dependent on the variable t. So our limits of integration, the interval where this overlap pattern is true is when t is between minus 1 and 3, but t, remember, is not the same as lambda. The integral now of these two waveforms is going to be the integral from lambda equaling 0, that's the lower limit, up to lambda equal to t plus 1. And now we simply need to pull out our integration capabilities and start integrating. So here we have 5, and then we have 2 over minus 2e to the minus 2 lambda, and we're evaluating that at 0 and t plus 1, which now says that we have minus 5 times e to the minus 2, t plus 1 minus e to the 0, or that's now 5, 1 minus e to the minus 2, t plus 1. Or, if I can write that a little bit more cleanly, I now have 5 times 1 minus e to the minus 2, t plus 1. And when is that true? Well, that's true when we establish the overlap picture to be valid, which was when t is between minus 1 and 3. That's now our partial overlap picture. We then have a total overlap. Again, it's easy maybe to quickly draw h of lambda, which is 2e to the minus 2 lambda. That hasn't changed, but now we want to look at the next unique overlap picture, which means that t minus 3, we need to pick t such that t minus 3 moves beyond lambda equal to 0, so that now we have a picture. Here is t plus 1, and here's t minus 3. Here's our interval of support for x of t minus lambda. Here is our interval of support for h of lambda, and we now want to say, when is this overlap going to occur? This picture happens under what conditions? Well, the condition that made this unique is when t minus 3 actually became bigger than 0. It slid past lambda equal to 0. So that now this is going to say that as long as t is greater than or equal to 3, this is the pattern that we have. The integrand hasn't changed. That's still 2e to the minus 2 lambda. That's h of lambda. X of t minus lambda is still 5. That hasn't changed. D lambda. Now what do we have? Well, we're not integrating from 3 to infinity. We're integrating over the values of lambda that establish where we have the blue hash and the red hash overlapping, or the cross-hatching. And the lower limit of that is now t minus 3, and the upper limit is t plus 1, which now allows us to conclude the same thing that we had before. We had 5, 2 over minus 2. The integral hasn't changed at all. It's just the limits of integration. The lower limit is now t minus 3. The upper limit is t plus 1. And if you work through all of that and distribute the negative sign into the argument of the bracketed expression, we end up with 5 e to the minus 2 times t minus 3 minus e to the minus 2 t plus 1. And again, if we factor out a minus 2t, e to the minus 2t from all of that, we would have 5 e to the minus 2t, and we're left with the first term being e to the 6, and the next term is minus e to the minus 2, and that's true for values of t that are bigger than 3. That was what allowed t minus 3 to move to the right of lambda equal to 0. So this is now valid, this expression for y of t, as long as t is greater than or equal to 3. That's now y of t, and I hope you can now see that the answer of convolving h with x with these functional forms now consists of 3 different functional expressions for y. We have y of t is equal to 0 when we had no overlap, and no overlap occurred when t was less than minus 1. Whoops. So now we have t less than minus 1. The next interval was when t was bigger than minus 1 and less than 3, and the last interval was when 3 is now, or t is bigger than or equal to 3. That's now the answer for this particular convolution problem, and somebody might be interested in what does that look like functionally. Well, remember that the time constant allows us to get a pretty good insight into what the shape of this exponential curve might look like. The time constant is available to us from e to the minus 2t. We need the 2t to equal, or the value of t, such that that's equal to 1 to get our time constant. So in this case, we're looking at 2t when t is equal to tau equaling 1, or tau, 2 tau is equal to 1, or tau is equal to 1/2. Or in 5 tau, which is 5/2, or in 2.5 units of time, we will have reached essentially a steady state. And in this case, this particular pulse is on for 4 units of time. So in that duration, we will actually get up to close to being equal to 5 if you look at this particular part of y of t. And if we sketch that, then that's what I'm sketching in red. Here is our pulse waveform, x of t. That's on from -1 to 3. And the red curve now shows that when we reach 2.5 units of time beyond, so here's 1 unit, here's a second unit, and here's a half unit. So now we're up to 1.5. By that point, we should be very close to this maximum value of 5 for x of t. And then we turn off the pulse and wait another 5 time constants, or until we get to 2.5 plus 3, or 5.5, and then we're effectively down to our final value, which is nothing. And now we have this shark fin type response to this pulse, blue, as our input, and the red is our output. If we changed the low-pass filter to have a wider bandwidth, or to have a pole at s equal to -10 instead of having a pole at s equal to -2, our time constant now changes. And so now let's just look at that. The red is low-pass filter number 1, where our time constant was 1/2. So a settling time, a 1% settling time, or 5 of those, or 5/2, or 2.5. If we changed our impulse response, which is really changing our low-pass filter, to have an RC time constant such that 1/RC is 10, then we have 10e to the -10t, or a time constant now tau equal to 1/10. 5 of those now says that in 1/2 of a second, we have reached our 1% settling time. That's what I've tried to indicate here in green. Now, in 1/2 of a second, we should be very close. So from -1 to -1/2, we should be almost at the final value of 5. Then we lock on to that value of 5 until it gets turned off at 3. And then 1/2 of a unit of time later, or at 3.5, our shark fin now for this wider bandwidth low-pass filter, we're passing more frequencies. Now it looks more and more like x of t than the red pulse. The red pulse didn't have as sharp of an impulse response, and now you can look at these impulse responses. 2e to the -2t does not look quite like the ideal impulse as 10e to the -10t might. So the closer h of t looks to the ideal impulse response, the more the output looks like the input. In this case, which of these waveforms looks more like the blue pulse, which was our impulse or input? The red doesn't look as close to the blue as the green. And the green had more of an ideal impulse for its impulse response than the red. That's now how we could combine or compute the convolution integral. And actually, we've finished that example with a little bit more intuition and insight into how to interpret the output response.